Hello, everyone. Hello. Thank you for being here. Thank you for attending this breakout session. Today, with my colleague and good friend Mauricio here, we are going to tell you how we drastically reduced our processing costs with Delta Lake and Spark at Amadeus. Our main goal in this talk will be to empower you with useful tools and ideas so that you can return to your own Spark applications and optimize them to reduce your costs. But before getting started, let's say a couple of words about us. We are Generoso Pagano and Mauricio Jost, and we are both principal data engineers at Amadeus, where we mostly have fun playing with Scala, Spark, and Delta Lake. Amadeus, our company, provides critical solutions for the travel industry worldwide. We connect airlines, travel agencies, hotels, airports, payment providers, and many more actors of the travel ecosystem. We give them the tools to actually do their business and serve their travelers better. Among the many solutions we offer to our customers, there are data analytics tools that really allow them to understand their business and optimize it using the power of data. And the product we work on with Mauricio and our team falls exactly in this category because we have a data pipeline based on Apache Spark structured streaming and running on Databricks that processes many different data feeds coming from several departments in Amadeus, like reservation, ticketing, the partial control system. And this pipeline transforms this data into easy-to-use relational databases based on Delta Lake. For example, let's say you are an airline and you would like to know which services sell best on a given route. Well, thanks to the information readily available in our databases, it is very easy to figure that out. So this product is actually very helpful for our customers, but it has pretty challenging requirements because we need to produce hundreds of these delta tables. We need to support several years of historical data depth. And on this data, we have to do history consolidation. Said otherwise, we need to go back in the past and update old records based on the new one we receive. So all of this makes for a pretty complex Spark application where there are a lot of joins and merges. And given the scale of Amadeus, we have thousands of Spark jobs. So this very application is the battleground of our cost reduction journey. A journey that is materialized by this single awesome picture. This graph shows the daily running cost of our application run on a pilot data feed, and it shows how this cost went down and down, milestone after milestone, thanks to the many optimizations that we have done. And we like this picture so much that we decided to use it as our agenda for today's talk. We will start our journey from a baseline that was pretty slow and expensive. So we'll explain how we addressed a tricky concurrency issue jumping to milestone 2. Then we'll share our first attempt at fighting the read amplification, introducing Z-order and dynamic file pruning. Then we'll explain how we tackled the write amplification, leveraging Predictive I with Photon and Deletion Vectors. And finally, we'll explain how we revised our history consolidation logic, achieving our target cost point. Overall, we reduced our costs by 99%. And this wasn't simply a cost reduction journey. This was also a learning journey for us. And that's why we are so happy today to be here and be able to share with you guys what we learned. So, Mauricio, let's start the journey.
Thank you, Generoso. You can hear me well. So this is milestone number 1. This is the baseline and the beginning of our journey. And this point in time got the honor of being called a milestone simply because there are 2 achievements that were really important. First of all, our application is functionally correct. It means that from a data point of view, everything looks fine and our customer will be satisfied. And also our application is technically stable. It means that our monitoring systems are looking good and we are just having all the unit tests passing. But when we put the application to the test and made it consume the largest feed we had available at the time, which we called the pilot, we noticed that the throughput was really below our expectations. And the metric that caught really our attention was the CPU usage, which was systematically below 10%. So we decided to take a look at that in first place. And you need to know that this is something that was unexpected because we have a JSON parsing stage in our application that was supposed to be CPU intensive. So at least we should see some spikes in the CPU usage curves, which we were not seeing. So we decided to take a look at this problem by using the Spark UI after the application had finished, because it was the tool that we had at hand. And it turned out that we faced a couple of difficulties. First of all, the Spark job that we were interested in had not been retained by the Spark UI. So this is something that Spark UI does in a best effort mode. It tries to keep the metrics of jobs for post-mortem analysis, but even if we tweaked some settings, we were not lucky. Also, we didn't have descriptions or names for the jobs, so it was really difficult for us to associate whatever we were seeing in the Spark UI with our code. And also, we didn't have enough information about the workers, and things like the stack trace or the logs, those informations just weren't there. So we decided to change slightly the approach and use this time the Spark UI, but while the application was running, so in live mode. And we placed ourselves in the moment in which that supposedly CPU-intensive Spark job had started, and we wondered, what are the workers doing then? And you guys, you'll be able to take a look at this in your own jobs. You can go to the Spark UI, check the executors, and we opened the thread dump for one of the executors, and we saw something like this. As you can see, the thread state for some of the threads, which are the task threads, was blocked in most of the cases. So these threads weren't doing anything useful. We decided to take a look at the thread logs, and we noticed that all these threads were waiting for the same resource to be freed. So we were actually, all of them were waiting for this shared lock, and we were in a very important thread contention situation. To put it graphically, we had all the task threads within a single worker JVM that were waiting for this resource, but only one of them was prevailing at a time. So bang, we got the smoking gun, we understood what was going on, and this was actually the reason why we had that low CPU usage. Before I can tell you how we fixed this problem, you would need to understand a bit more about the culprit. So it was a Scala closure using a third-party library for JSON parsing. I'm not going to mention the library. And it was going through a cache implementation that was, let's say, not behaving the way we would have expected under heavy concurrency conditions. And the alternatives we had, well, there were many alternatives, but the ones that we took a look at were just to move away from the Scala closure and use built-in SQL functions. But it turned out it was a very complicated thing to do. And we noticed that this library, we could change the cache implementation by just changing one single line of code. So we decided to do that. We did the change, and we retried, and the results were just amazing. So it was a very emotional moment, actually. The thread state became runnable, and the CPU usage became, so we saw these gorgeous plateaus hitting now the 80% of CPU usage. So this single line of code change took us to milestone number 2, where we observed a cost reduction of 77%. Of course, when compared to milestone number 1. We knew we were still far away from the cost target, and we knew that we would need more iterations to get there, and we had understood that it was very difficult for us to extract metrics and extract measurements from the application run, so we needed to work on that and make the investigations easier. And that's why we went through what we called a metrics unlocking phase, where we came up with a couple of best practices that we wanted to share with you so that you can improve your application. So the first best practice is try to reproduce performance problems in minimalistic notebooks. This is something that will allow you to iterate fast on the problem, understand it very well, see it from different angles, understand very well how to measure that problem, and eventually come up with a couple of solutions, and then choose the best solution according to the way you are measuring it. And this is a discovery and an approach that we believe in so much that we decided to open source a project that is called Performance Hikes for Apache Spark, or Perf Hikes for short. It's available on GitHub, and there you will be able to find a collection of notebooks that you can play with in either Databricks or using the Spark shell, where you will be able to play a problem, play the solution we have found for that problem, and be able to, with the instructions that we give via documentation, measure on your own the before and the after situation. And this is something that has proven to be very, very useful for us. And whenever you see an icon like this one, this bag full of useful notebooks, it means that, and whenever you see it throughout the presentation, it means that you are in presence of a scenario that you can play with on your own. So make sure to check it out. Second recommendation, name every single Spark job that you have in your code. This will allow you to associate whatever you have in the Spark UI in terms of jobs with whatever your code is. And this is something that is as easy as using a method before the action is called. Its name is setJobDescription on the Spark context, and it will give something like that in the Spark UI. So it's so simple to do. We use it extensively in the project. It's something that really takes no time and will help you a great deal. Third recommendation, persist Spark events for post-mortem analysis. This is something that we did because of two reasons. The first reason is that we wanted to get rid of this problem with the retention of the jobs metrics on our Spark UI. We wanted to have that information available at all times, unconditionally. And the second reason is because we wanted to actually run queries on those metrics and be able to answer questions like, am I having a spill in my application run? And if yes, which job exactly is spilling at a given moment in time? There are certainly multiple ways to do that, but we have shared with you, again in the project, a very easy way to do it that is based on a custom Spark listener that we invite you to take a look. We believe it's a great way to get started. And then fourth recommendation, try to use cluster or pool tags as offered by your cloud provider so that you can measure the cost of your deployments, compare them, and eventually, and also do a breakdown on the different cost of the different components of your application run. And you'll be able to answer questions like, what are the costs of the network egress that you can associate with the cost of the writes? This is something you will see. We will use a bit in the rest of the presentation. And now that we are much, much better prepared to extract metrics from our application runs, let's go back to the optimization journey.
Thank you, Mauricio. Yes, moving on with our journey. So the main observations at this point in time were the following. The network was the biggest chunk of the cost. It was 70%, really huge. And our application was doing a lot of joins, joining small input batches with big tables. And our big tables didn't have any particular data layout that could help with data skipping. So the intuition we had at this point was that maybe we were suffering from read amplification. Basically, we were reading way more data than actually needed to do our joins. This was the hypothesis, yes, but how did we assess that in a rigorous scientific way? Well, let's say, for example, we want to investigate this join between a big and a small table, where I'm doing a predicate on the small side. So thanks to the instrumentation that we have done in our code, as Mauricio just explained, it is now very easy to go to the Spark UI SQL Data Frame tab and find the SQL query corresponding to this join, simply looking for its name. Easy. And once we have the query, it's now possible to explore the Spark plan. And we can observe that this join, a broadcast hash join, is only producing 100 rows. But if we look at the scan parquet node corresponding to the big table before doing the join, we observe that we are not pruning any file. We are reading the whole table, more than 12 million rows, just to have 100 matches in the join. So this situation, which has been reproduced in our GitHub repository, performance hikes, by the way, was happening all the time in all our joins. So clearly, there was something to do. We needed to do something to have some data skipping to avoid reading the whole table. And that's why we decided to introduce Z-order and dynamic file pruning. Let's start with z-ordering. Z-ordering is a technique that collocates related data in the same set of files so that it is possible to do some data skipping. You do a z-order on a delta table in the context of an optimize, as I'm doing here in this simple example, where I am optimizing the airports table, z-ordering by the country code column. I'm using a single column here. I could use more than one, but beware that the more columns you add for your z-ordering, the less effective the colocality will be. One very important thing to know is that you must have column statistics enabled on the column you're using for z-ordering. Why? Well, if you don't, you will get an error. And if you suppress the error, the whole z-ordering thing will be a complete waste of time and resources, because without statistics, it will not help much. So pay attention, please, to these two delta table properties that control exactly on which columns you are computing statistics. And if you want to see with your own eyes the effects of z-ordering on your table, a nice way to do so is querying directly the delta log of your table and displaying the min and max value for your z-ordering column. I have done this exercise for our airports table, and we can appreciate how our country codes are well sorted and collocated among the different Parquet files. So, for example, if I want to fetch all the rows that contain the country code AR, Argentina, it is very easy to understand that I only need to read the first Parquet file, because all the other files simply will not contain AR. So this colocality can be really used to enhance data skipping, can be really leveraged by data skipping algorithms like dynamic file pruning, which is a data skipping technique only available on Databricks that is particularly useful in this very kind of joins, where I am joining a big and a small table. Let's assume now in this example that the big table has been z-ordered on the join key. So what dynamic file pruning is able to do is creating a dynamic filter based on the key values in the small table, and then pushing down this filter to the scan phase of the big table so that only the files containing the keys that will contribute to the join will be read, not all of them. So here on the right, we have what we have seen before, the scan Parquet node for the big table without DFP and z-order, and we see that we are reading the whole table. On the right, instead, we have the same scan Parquet node, but with DFP and z-order this time. And we can appreciate that we are reading one single file out of 18. So the reduction in the amount of data we are reading is huge. When DFP kicks in, it could really change the rules of the game. But in order for it to kick in, well, you have to meet some constraints. First of all, you need to be on Databricks. Then your join should be a broadcast hash join. And then your configuration should be properly set. In particular, DFP should be enabled. And these two thresholds should be low enough for DFP to take action. So anyway, all the code examples, all the configuration are available as always on our GitHub repository. So be sure to check it out if you're interested. But back to our journey. So we said we introduced z-order and DFP for our joins, and the result we got were pretty good because we reduced our cost by 40%, and most of it was the network, as expected. What was not expected is this bad surprise that we had, because data skipping increased, yes, but it was still pretty low, way below expectations. Why? Well, because our pilot data feed had pretty nasty keys. Even in a small input batch, those keys there were hitting most of the files. So even with DFP, we were obliged to read those files. So where did the cost reduction come from then? Well, it came actually from the data compression that we achieved thanks to z-order and optimize. Why? Well, because this key we are z-ordering on is actually the functional key of functional entities that have many versions. So z-order on this key, we are putting together close to each other in the same file, many versions for the same entity. So these versions will be pretty similar to each other. So the potential for data compression is huge. That's why we got smaller files, a smaller network footprint, smaller costs. So this was a first attempt fighting read amplification. We put this bet on hold for the moment, and we start focusing on the right operations for the rest of the journey.
Thank you, Janet. So at this point in time, we were wondering whether we were suffering from write amplification, whether we were writing more data than we actually wanted to. And the reason why we started focusing on that was because of the following observations. We knew functionally that we were expected to update roughly 1% of the rows that we had in our tables in every run of our application. So this relates to the cost of the writes. And because we hadn't yet solved the read amplification problem, we were expected to read roughly 90% of the rows of our tables in every single run. So if you take a look at this, you would expect that the cost of the writes, they should be negligible compared to the overall cost of the network. But it wasn't the case. So it was actually the opposite. We measure a really high cost of the writes, and we measured this using the network egress costs that we presented before. We didn't really know why it was the case, but we had an hypothesis, and we thought it had to do with copy on write. So copy on write is a merge strategy. It's available on Delta Lake, and it's known to be a bit harsh on the write amplification. And let me share an example with you so that you can see. Let's say that you have a Delta table. Let's say that it's made out of multiple Parquet files. And let's say that you want to update roughly 1% of the rows in that table, and that those are spread on 2 out of the 3 Parquet files. If you did a merge with those constraints using copy on write, what would happen is that you would end up completely rewriting 2 out of the 3 files. You would write the records that were changed, but you would copy along as well the records that didn't change at all. And this is write amplification. You wanted to update 1% of the rows that we had, but you ended up completely rewriting 2/3 out of the rows. So we didn't know whether it was the case for our application, but thanks to the project, we managed to reproduce a scenario and understand that we could assess the write amplification using history operation metrics. So let me show how that looks like. We reproduce in the scenario a simple absurd that looks like this on a delta table. And then we took that delta table, we observed its history, and with some manipulation, we got some operation metrics, the 2 that you see here, the number of source rows and the number of output rows. The first one represents how many rows you wanted to update, the intention. And the second one represents how many rows you actually ended up rewriting. What physically really happened. And as you can see, there is a big difference. You wanted to update 10 rows, but you ended up physically writing 600 rows. So there is a problem there. Using this method, we checked in our production data whether this was happening, and it was the case. This was what was going on in our case. But thanks to Data and AI Summit 2023, we understood that copy on write was not the only choice. There was as well merge on read merge strategy. And it was supposed to be less harsh on the write amplification. And it came under the name of deletion vectors. So we decided to retry this time, but enabling the deletion vectors, and the results you can see are pretty good. We ended up now using deletion vectors, writing as much data as we actually wanted to. It was the good thing to go for. We needed these deletion vectors for the merges. And because of the Databricks runtime that we were using, we needed to enable Photon. So hopefully by using deletion vectors, we would have resolved the write amplification problem, and everything should look good, and the cost should be decreasing. But it wasn't the case. We measured that, and the cost had actually increased. We didn't know really what was going on. So we decided to get in touch with people from Databricks account team in Paris who helped us figure out what was going on. So now it's an opportunity to thank Florian, Amar, and Laurent who helped us. They put us in touch with a Databricks consultant called Peter Stern who helped us figure out what was going on exactly. And long story short, Photon was being underused. There are 2 reasons we know of why Photon may be underused. The first reason is that you have a SQL query that is not fully supported by Photon. And let me show to you how to figure out whether that's your case or not. we reproduce in the project a SQL query that is similar, but in one case we implemented it using a UDF, which is not supported by Photon, and in the other case using a built-in SQL function, which is. And if you go to the Spark UI and you take a look at the execution plan, what you will see is that the project operator will be blue, which means that Photon is not doing any optimization. If you go to the details, you'll have some more information about the why. However, if you did the same thing for the built-in one, what would happen is that the project operator will be yellow, which means that Photon is doing an optimization. And if you go to the details, well, you'll have a confirmation of that. But it wasn't our case. What we had was an incompatible Spark setting. And what we had was actually, we had disabled the off-heap memory because of historical reason. And this was actually preventing Photon from working correctly. And we figured that out by taking a look at the details of any SQL query we had in our application. So now we enabled the off-heap, and the results were pretty good. The deletion vectors now merged. They were working correctly, and Photon was being much better used. So this took us to milestone number 4. With Photon and deletion vectors, we measured a cost reduction of 50% for our scenario compared to milestone number 3. As per discussion with the Databricks consultant, we understood that our sparse settings, they were good enough. So it was now time to go focus on the read amplification problem, which was still our biggest fish, but this time with a slightly different approach.
Yes, thank you, Mauricio. Yes, indeed, we followed our Databricks consultant's advice, and we deep dived into our history consolidation logic, which is the place where all this read amplification was going on. And to explain it to you, this logic is pretty similar to the SCD type 2 logic that maybe many of you are already familiar with. But just to be all on the same page, let's see with a simple example. Let's imagine we have a table like this one, where every row represents a version for a given key. So here, for example, I have versions 1, 2, 3 for the key K1. I also have this column, last, that is a flag that tells me if a given version is the last one received for a given key. So when a new version for K1 arrives, what we want to do is change the last flag for version 3, the current last version, from true to false, and then add the new line with version 4 flagged as the last one. Easy. We can implement this with Delta with 2 steps. First, we need to compute a patch based on the input where we will have version 4 with the flag set to true, version 3 flag set to false, and then we merge this patch into the table to achieve this final desired state. This patch computation can be implemented with a join and a window function, but I'm not giving all the details here because everything is available on our GitHub project, Performance Hikes. So the main message here is that with this approach, we have a big problem. Okay, let's see. We know that our table is composed by a bunch of Parquet files in a folder. And we have mentioned before that for each input batch, basically, most files end up containing, unfortunately, at least one of the input keys. So to do our joins and our merges, we have to read those files. And that's why we have such a high read amplification. But if we look closer at our algorithm, we realize that we don't need to read all the versions for a key to implement this logic. What we really need to read is only that version, version 3 in this example, where the flag last is set to true when the new batch of data arrives. So leveraging this observation and also the fact that we know that we have many versions for each key, we decided to partition this table on the last column. So now the data layout of the table is the following. We have one big partition where we have all the rows where last is false. And for us, it was 97% of the data because, as I said, we have many historical versions for a key. And then we have a small partition where last is true that for us was simply 3% of the data. So now, with this data layout, when the new batch of data arrives, we can be way smarter because we know that we only need to read the small partition, the rows where last is true. So we can safely put this condition, table.last equal true, in our joins and merges. And thanks to this, we will only read at most 3% of the data. And also the other operations of the merge will be very efficient because the transition from true to false of this flag is simply a soft delete in the small partition. Remember, we have deletion vectors now, and an append in the big one. And adding a new line to the table where, well, it is simply an append operation in the small partition. So at no point in time, we need to read the big partition, and that's the real game changer. Because if we want to wrap up, we are only reading 3% of the data. We are only doing very efficient operations like soft delete and append. So when we implemented this approach in our production workload, the results were dramatic. Really, we reduced our costs by 90% compared to the previous milestone because the read amplification basically went away. So the network costs went down, the processing time went down, and the Databricks runtime cost went down. Everything went down, and we finally achieved our target cost point. There is an important lesson learned here. And the lesson is that when the expected gain of purely technical changes become low, it is maybe time to deep dive into the business logic you are trying to put in place with your data, because it is only by mastering both the technical features and the functional sides of your application that you really achieve the best performance. So, with this, we arrive at the end of our journey. What's next now? Well, there's today. Today and the fact of sharing our journey and what we have learned with you guys in this awesome summit. So now I can pass it to Mauricio for the conclusions.
Thank you, Jenny. So this journey has definitely offered us wonderful moments. Today is one of these moments. We are super happy to be sharing this with you. We addressed our thread contention problem, the read amplification using Z-order, dynamic file pruning, and this revised history consolidation, and write amplification using Photon and deletion vectors. All in all, from milestone number 1 to 5, we got to a 99% of cost reductions. And let me share with you, before we conclude the session, a couple of lessons that we have learned along the way. First of all, be ready to iterate, especially if you're planning to embark upon a journey like this one. Get ready. So understand that even if an application that you have is cost-effective and competitive today, it may not be tomorrow. The platform will evolve, your competition will evolve, so get ready to keep measuring your costs and keep learning about the new features coming. While you are in one of the rounds of investigations and optimizations, do investigations in a rigorous manner. Try to formulate hypotheses, try to validate those hypotheses, document whatever metrics you have. That has left us not only with these great results, this sort of scientific approach, but really with a ton of tools and knowledge that will certainly, I'm sure, will definitely help us go even further in this cost reduction journey. If you're stuck, just ask for help, that's okay. Just try to help people helping you by reproducing the problem that you're having in some minimalistic notebooks that will help them. And at last, I would say, and the most important point, allow yourself to be ambitious, allow yourself to dream, because after all, even as I think we have shown to you, even cost reductions of 99% are possible. So it's been really a pleasure to be here. Thank you very much.